There is one more component that is used in practically every electronic device today and makes all our technologies possible. It is another application of semiconductor technology, and you certainly heard about it at some point: the transistor. The transistor is like a switch that can turn on and off current flow. However, it does so without needing any mechanical components. We will first revise the PN-junction and then discuss the first form of transistors, the BJTs. We'll dive into MOSFETs and their different variations, and finally, we will look at the schematic symbols of the various transistor types. Remember the PN junction that is within every diode. A p-doped semiconductor is next to an n-doped semiconductor. In the border region, electrons move from the n side to the p side to fill up some electron holes. Through that, a slim region on the n side becomes slightly positively charged, while a slim region on the p side becomes slightly negatively charged. There is an electric field that goes from the n to the p side, which makes it hard for more electrons to move from the n to the p side. If we apply a forward bias voltage of more than 0.7 volts, the depletion region shrinks and the material becomes conductive. In reverse bias, the electrons are attracted towards the plus pole, the depletion region increases and no current can flow. The simplest form of a transistor is the BJT, the Bipolar Junction Transistor. It works by adding another N or P-doped semiconductor to a PN junction. If we add an N region, we get an NPN transistor. And if we add a P region, we get a PNP transistor. Let's analyze the NPN transistor. The transistor consists of 3 ports. One is connected to the first N region, which is called the emitter. Another is connected to the second N region and is called the collector. And the port connected to the P region is called the base. We can think about a transistor as consisting of 2 diodes facing in opposite directions. If we apply a voltage from the emitter to the collector, one of them is always in reverse bias and won't allow current to flow. However, if we apply a positive voltage to the P region, electrons from the N region are attracted to the base. Through that, the depletion area decreases and the electron holes of the P region fill up. Because there is no depletion region anymore, the electrons from the first N region are attracted to the plus pole of the battery connected from the emitter to the collector, and current can flow between the emitter and the collector. The higher the current on the base, the less the depletion region, the less the resistance between emitter and collector, and the higher the current flow between emitter and collector. The collector-emitter current is magnitudes higher than the base current. In fact, the base current and the collector-emitter current are proportionally linked by the proportionality constant, HFE, that we can find in datasheets of transistors. ICE is equal to IB times HFE. A more advanced transistor version is the MOSFET, which is used in almost every integrated circuit today. Your laptop and phone contain billions of them, and with each passing year, the sizes shrink drastically. Today, the smallest ones are only 7 to 10 nanometers small. A silicon atom is 0.2 nanometers tall, which clarifies how tiny these transistors are today. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. There are many different types of MOSFETs. Firstly, we can separate them into enhancement and depletion type MOSFETs, and then we can subdivide them into N-channel and P-channel MOSFETs. Let's look at the N-channel enhancement type MOSFET first. It again consists of 3 regions, 2 N regions and 1 P region. However, this type of transistor consists of 4 pins. The emitter equivalent is called the source and is attached to the first N region. The collector equivalent is called the drain and is connected to the second N region. The base equivalent is called the gate and is connected to the P region, but with an isolator or dielectric between the gate and the P region. The 4th pin is connected across the gate and internally connects to the source. If we connect a battery between the source and drain, there would be no current flow, as one of the PN junctions is in reverse bias. However, if we additionally apply a voltage to the gate pin, an electric field is created between the substrate pole and the dielectric. electrons move from the N-junction to the dielectric and fill up some electron holes in the P region. The more voltage we apply at the gate, the more electrons are attracted. This plate works similar to a capacitor. At some point, there are freely moving electrons in the upper part of the P region, which creates a tunnel between the two N regions in which electrons can move. This illustration explains the primary difference between a BJT and a MOSFET. A MOSFET is voltage controlled rather than current controlled, meaning no current flows through the gate. However, a brief current burst is needed to charge the gate's capacitance. When we increase the drain source voltage VDS, the drain source current IDS increases linearly at the beginning. However, the second N region removes electrons from its border that travel to the plus pole of the battery, while holes on the other side move to the substrate body. Therefore, the depletion region of the second N region increases. Through that, with increased drain source voltage, the tunnel becomes narrower again, and the current does not increase linearly anymore, but reaches a saturation, which we call saturation current. However, by increasing the gate voltage, the tunnel becomes wider. Therefore, we can entirely control the drain source current by the voltage we apply to the gate. This characteristic makes the MOSFET ultra useful and gives it another name, a so-called voltage controlling device. The P-channel enhancement type MOSFET operates similarly to the N-channel but with reverse polarities. It consists of two P regions and one N region. To switch on the P-channel enhancement type MOSFET, we have to apply a negative voltage to the gate. The negative voltage creates an electric field that attracts holes from the P region into the N region near the gate. These holes accumulate in the N region, forming a conductive path or channel between the source and the drain. With the channel formed, holes can move from the source to the drain when a voltage is applied between them, allowing current to flow through the MOSFET. Source and drain are also switched. The source is connected to the positive pole while the drain is connected to the negative pole. A PNP BJT works in a similar way but is current controlled rather than voltage controlled. In a PNP transistor, when a small current is applied to the base, it allows a larger current to flow from the emitter to the collector. We will also briefly discuss in what ways an N-channel depletion type MOSFET is different to the enhancement type. In the depletion type MOSFET, we already have a pre-existing tunnel manufactured into the MOSFET, which means that without the gate turned on, current can flow from the source to the drain. By applying a negative gate voltage to the depletion type MOSFET, the depletion region decreases and the tunnel becomes narrower to the point of being able to turn the MOSFET completely off by applying a negative voltage to the gate. Now let's take a look at the circuit symbols of these different transistor types. Let's first look at the bipolar junction transistor symbols. In the NPN transistor symbol, the arrow points outward from the base to the emitter, while in a PNP transistor, the arrow points inward from the emitter to the base. The letters E, B, and C represent the emitter, base, and collector terminals, respectively. Next up, let's take a look at the MOSFET symbols. In the N-channel MOSFET symbol, the arrow points from source inward to the gate. For the P-channel MOSFET, the arrow points from the gate to the source. In all cases, the third pin on the right side of the symbol represents the connection between the substrate and the source. For depletion type MOSFETs, the three terminals on the right hand side are connected, indicating the pre-manufactured terminal. The letters S, D, and G represent the source, drain, and gate terminals of MOSFETs respectively. BJTs operate as current-controlled devices relying on a continuous base emitter current to remain active. In contrast, MOSFETs are voltage-driven, making them inherently more effective. This voltage-driven characteristic grants MOSFETs several advantages. They boast lower consumption and superior switching efficiency compared to BJTs. Additionally, MOSFETs typically offer faster switching speeds, making them ideal for high-frequency applications. Moreover, MOSFETs exhibit better thermal stability and can handle higher power density than BJTs, contributing to their widespread use in modern electronics. Furthermore, MOSFETs are more scalable, allowing for easy integration into advanced semiconductor technologies. A transistor is another semiconductor. We can use it as a switch or as a voltage controlling device in a circuit. One of its simplest forms is the BJT, which is created by adding an N or a P region to a PN-junction. For an NPN type BJT, we get three connections called the emitter, connected to the first N region, the collector, connected to the second N region, and the base, attached to the P region. The two PN junctions function as two opposite facing diodes. If we apply a voltage from the emitter to the collector, one of them is in reverse bias, which means that no current can flow. However, if we apply a positive voltage to the base, electrons are attracted from the N region and fill up some of the electron holes of the P region. If enough voltage is applied, there are freely moving electrons in the P region, which makes it conductive. Consequently, current can flow from the emitter to the collector. The higher the base emitter current, the more freely moving electrons and the higher the emitter collector current. The two currents are linked through the proportionality HAV. Another form is the MOSFET, metal oxide semiconductor field effect transistor. An N-channel enhancement type MOSFET consists of 4 ports: source, gate, drain and substrate body. The substrate port is internally attached to the source pin. The source is connected to the first N region, the drain to the second, and the gate is connected to the P region. However, between the gate and the P region there is a dielectric which allows no current to flow, and opposite the gate is the substrate body plate. When we apply a voltage between the gate and the source, an electric field between the gate and the substrate body is created. This electric field draws electrons from the N region to the plate, which again fills up electron holes, and if enough voltage is applied, the plate becomes negatively charged as in a capacitor. This charged region creates a tunnel between the two N regions, which makes current flow possible. By increasing the drain source voltage, the current rises linearly in the ohmic region of the transistor. The higher the drain source voltage gets, the larger the depletion region on the drain N region becomes because it is in reverse bias. This enlargement in the depletion area limits the drain source current, which we call the saturation current. The saturation current changes with the applied voltage to the gate, as the gate voltage can enlarge the tunnel. For a P-channel MOSFET, the voltage must be applied with the source at a higher potential than the drain. To turn the P-channel MOSFET on, the gate voltage must be lower than the source voltage. This means that a negative voltage relative to the source needs to be applied to the gate to create this channel between the source and the drain. Finally, in the N-channel depletion type MOSFET, a conductive channel or tunnel is pre-manufactured into the device. By applying a negative voltage to the gate, the channel can be narrowed or closed, reducing or stopping the current flow. MOSFETs have faster switching speeds, higher efficiency and are more scalable, leading to their more frequent use compared to BJTs. The full course is available on Udemy.